My name is Simon and I'm going to present the paper The ELBO of Variational Autoencoders Converges to a Sum of Entropies. This is joint work together with Dennis Forster, Dimitri Velichko, Zhenwen Dai, Asya Fischer and Jörg Lücke. Okay, let's directly step into the paper. The main result considers the ELBO, so the central learning objective of variational autoencoders. And in this paper we show that at convergence the evidence lower bound is given as a sum of three entropies: the average encoder entropy, the negative prior entropy, and the negative decoder entropy. Why that is, how we derive this result, and how you could use it will be the topic of this talk. I'll just give a very short introduction to VAEs, discuss roughly the ELBO, and then we are ready to dive into the theoretical results and the applications. Okay. Variational autoencoders are a popular probabilistic framework that can serve as a generative model, allow to learn useful representations for downstream tasks, can perform anomaly detection, disentanglement, and so on. To this end, we consider vanilla Gaussian variational autoencoders, termed VAE1 in the paper. So we have a standard normal prior, a decoder which has a mean, parameterized as a deep neural network. We have the scaled identity as a covariance matrix, and sigma here is a learnable parameter. The encoder has two DNNs, one for its mean and one for its diagonal covariance matrix. Let us discuss one or two aspects of variational autoencoders. In contrast to autoencoders, the mappings that are learned by encoder and decoder are by definition stochastic. That is, a data instance is encoded as some Gaussian distribution, and in latent space, and mean and covariance are estimated by the encoder. We can then sample from that to thereafter decode it back to data space. In the ELBO, we have a KL divergence that tries to ensure that these embeddings in latent space are close to the predefined prior, such that at convergence or after training, we can then sample from this prior to decode those latent codes in order to obtain new data instances. Ideally, we would like to train a variational autoencoder using the maximum likelihood method. However, the likelihood itself is not tractable. And this is where the famous evidence lower bound or variation free energy comes into play. As the name suggests, the ELBO is a lower bound on the log likelihood. And this here is arguably its most famous form. So we have a reconstruction score and the regularization score I just mentioned. Surely there are various formulations of the ELBO out there. And using this one here, for example, we see that the encoder entropy is already part of the ELBO. Let's have a bit of a closer look at the ELBO of Variational Autoencoder 1. So we see that we have one term here that looks already quite like a Gaussian entropy. And then we have the reconstruction error. So the performance of this encoder-decoder channel weighted by the inverse of the variance. And as both here, the encoder and the prior are Gaussian distributions, of course, the Kullback-Leibler divergence, and therefore the regularization score has closed form solution. So we're now ready to discuss the theoretical result in a bit more detail. Consider training a vanilla VAE as just introduced on some dataset. At all stationary points of the ELBO, we can then show that the value of the ELBO decomposes into three values: the average encoder entropy, the negative prior entropy, and the negative decoder entropy. The last line here makes use of the closed form solution for Gaussian entropies. The idea of the proof is to consider a reparameterized version of VAE1. So we allow a model to explicitly learn the prior variances. Such a VAE we term VAE2. We ensure that VAE1 and VAE2 indeed parameterize the very same distributions by restricting the decoder architecture. We can then show for VAE2 term-wise convergence by invoking optimality conditions on the covariances of decoder and prior entropy. We then transform the result back from VAE2 to the case of the vanilla VAE with a non-learnable prior variance. Please see the paper for the further details on the proof. Let's consider some ideas on this result. First of all, it's an exact analytical result. Moreover, it holds at global and local optima. In particular, we just require very small fractions of parameters to converge. We place very mild assumptions on the network architectures. So in essence, we just require that the first layer of the decoder is indeed linear. And the result holds for the infinite data limit, but also for finite data sizes. So to wrap this up, the result really holds in practical scenarios. And this is also what we observe in practice. In our experiments, for example, with linear VAEs or with multi-layer perceptron on a MNIST dataset, we see a nice correspondence between the lower bound, so Monte Carlo approximation of the ELBO, and our three entropies expressions after convergence of the variances. Same holds for the additional experiments that we conducted on ZUSI, a high-dimensional physics dataset, and with convolutional architectures on the CELEB-A dataset. The results might also be a bit surprising, as neither the likelihood, which is not even tractable, nor the ELBO are closed form during training. This stems from the first term in the ELBO, so this reconstruction score. So one perspective on the result is that all the relevant information, that is the solution of these high-dimensional integrals, are already captured in the variance parameters at convergence, or equivalently in the entropies. This is made explicit by the analytical solution to the optimal decoder variance here, which resembles the reconstruction performance of the encoder-decoder channel. If we, in addition, consider learnable prior variances, as in the case of VAE2, we see that the optimal prior variances converge to the second moment of the latent codes. With this, we have the first application of our entropy result already at hand, that is, the estimation of the training ELBO. The only term that still needs to be computed is the first one here, so the average encoder entropy, which depends on the data. The other terms here, the prior entropy and the decoder entropy, contain all the other relevant information to compute the ELBO estimates. We can see this here in our CELEB-A experiments. So the naive Monte Carlo approximation of the ELBO is quite noisy and requires quite some samples to deliver precise estimates. In contrast to our three entropies expression, where already very small sample sizes provide precise estimates of the true ELBO value. We investigated potential generalizations of our result. First generalization that we found is that the result carries over to more complex VAE distributions. That is, if we consider the decoder covariance to be replaced by a deep neural network that implements the diagonal elements of this diagonal covariance matrix, which is now dependent on the latent code, then indeed we are able to generalize the result. The proof is much more intricate, but we see that it's indeed a generalization of the theorem for VAE1. So encoder entropy and prior entropy stay unchanged, but here, instead of just the plain decoder entropy, we have the average expected decoder entropy. So in this sense, a true generalization of our result. We found that the result also carries over to many members of the exponential family. Please see our paper, Theorem 3 in particular, and definition C in the paper by Jörg Lücke, so concurrent work, for the exact prerequisites and criterions that you have to meet, such that a convergence result to entropies also carries over for your generative model of interest. Okay, let's now proceed to the applications. The first one, we already discussed that, so the estimation of the training ELBO using the model entropies, but also both scores, namely the reconstruction and the regularization, are now given in terms of entropies. So we encourage you to monitor entropies throughout training, and this comes without any additional computation overhead, as the variances of your model should be already at hand anyway. A first use case of why it is beneficial to consider the entropy-based formulations of the scores in the ELBO is given by the analysis of the posterior collapse phenomenon. We will make use of the regularization score in the ELBO, that's the negative KL divergence, to define and monitor posterior collapse. In the case of the entropy result, it's simply the gap between average encoder entropy and prior entropy. Posterior collapse itself is an empirically observed phenomenon, in which latent variables collapse to their corresponding prior variable, and in this sense are pruned out as they do not encode any information about the input anymore. The phenomenon itself is not well understood or even well defined. For discussion, see for example the Lucas et al. Paper, in which they propose to measure posterior collapse based on the KL divergence. However, you need to track then both mean and variance of the corresponding variables. With knowledge of the entropy result, we can simplify that by thresholding the gap between average encoder entropy and prior entropy. So the measurement only depends on the variance parameters. For a standard Gaussian variable, the entropy is roughly equal to 1.42. So in this sense, we can simply choose a threshold set to 1 and consider a latent variable collapsed if the encoder entropy exceeds this value 1. We conducted experiments to see this entropy-based measurement of posterior collapse in practice. We created a data set for which we can actively control the intrinsic dimensionality of the data. So in this sense, we created synthesized manifold data, and we see that during optimization, a reasonable amount of latents are pruned out. The same also goes for the SUSY dataset, where we have also an idea about the intrinsic dimensionality of the data. We like to strengthen the point that this measurement only relies on the variances of the encoder and, if learnable, the prior variances. So in this sense, the result also carries over to situations where we restrict the decoder variance to some suboptimal parameters, as it's often observed in practice. Another use case is the model selection in streaming applications. We consider linear variational autoencoders, and we can then derive a corollary such that the ELBO is simply given here again, as we know it in the case of the vanilla VAE, by the variances. This formula is already simplified, so this term, the first term, already captured the difference between encoder and prior entropy. PCA is frequently used as a pre-processing step in streaming applications, so in online fashion, and we conducted experiments for model selection using the big score, and we see that we are able to perform reliable low variance model selection just with the entropy-based expressions. So when seeing this formula again, independent of the data, just by knowledge of the model parameters, the model variance parameters. Let me briefly summarize the contributions of our paper. We show that the ELBO decomposes into 3 entropies at convergence. We also give an information theoretical interpretation of that in the paper, so check this out if you're interested. We show that characteristic points of the optimization landscape are indeed described by entropy relations. We made use of that by defining a simple measure for posterior collapse that turns out very handy in practice, and are able to perform reliable and fast model selection in linear VAE case. So overall, it seems that the entropies are indeed the natural figures to analyze when optimizing or analyzing variational autoencoders. We hope you find our work interesting, so please check out our paper, and we thank you for your attention and looking forward to see you at the conference.